Hi everyone. Today I'll be talking about the Diels Alder reaction. This is a cycloaddition reaction, and it's one of the main pericyclic reactions that you'll learn in organic chemistry too. So what happens in a Diels Alder reaction is, again, I said it's cycloaddition. So we start with two molecules, and then we end up with one cyclic molecule. So we add a cyclic molecule to the overall system. So it's called cycloaddition. And the way that we see this is we usually see a conjugated diene. We could also see conjugated trienes, but I'll get into that in a second, plus a double bond. And we can, or plus something with a double bond rather. So let's say like it looks like, let's say it looks like this. And we have X here and Y here. So when we do this pericyclic reaction, what will happen is that these two will combine together to make a cyclic compound. And so what happens here? I'm going to go ahead and draw out the mechanism. The way that I like to think about it is each pair of pi electrons move in a clockwise or counterclockwise fashion. So this pi electron pair goes out here. This one goes here, and then this one takes up the space that the other pi electrons left, and we end up with a cycloaddition. So we have 1, 2, 3, 4, 5, 6. So we're going to have 1, 2, 3, 4, 5, 6. And so here's Y, here's X. These would have stereochemistry, but I'll get into that in a little bit. So we can see here that now there's a double bond right here. So I'm going to show you where each of those pi electrons went. So this first pi electron added 2 to make this sigma bond. This pi electron pair made this sigma bond, and finally this pi electron pair made this new double bond. We can see that the original molecules from our reactants are here and here. We can see what happened is the pi electron sort of unfolded to make two new sigma bonds and make our cyclic compound. And so this system, we would call it a 4pi 2pi system, because we got 4 pi electrons from one molecule, and we got 2 pi electrons from the other molecule. There are some Diels Alder reactions that will use different pi systems, such as a 6 pi and a 2 pi system, or even an 8 pi and something else system. I'm going to show you a 6 pi 2 pi system right now. So let me just clear this. So in a 6 pi 2 pi system, we are going to use something called a triene. So triene instead of a diene. But essentially, the idea is still the same. A triene has 3 conjugated double bonds. So let's see if I can draw this from memory. So we have 1 here, 1 here, and 1 here. And you can see they're completely conjugated. They all have only a single sigma bond between each other. And then let's say that we have our, let's say that we just have the same, or a similar single double bond molecule right here. So this would be a 6 pi and a 2 pi system. And the way that this would work is exactly the same. So this one moves out here, this one moves here, this one moves here, and this one moves here. And we end up with 1, 2, 3, 4, 5, 6, 7. Ooh, that's going to be fun to draw for me. 1, 2, 3, 4, 5, 6, 7. Okay, that'll just have to be good enough. But essentially, we can see that oops, let me use a different color. This double bond moved right here. This double bond moved right here. I find it a little bit easier to draw the new pi bonds rather than drawing the new sigma bonds. So we can see here, okay, so here's the new sigma bond, and here's a new, oops. Oh, I miscounted. 1, 2, 3, 4, 5, 6, 7, 8. Hold on, let me pause the recording and I'll just redraw this for you. Okay, I'm back with the correct number of carbons now. Essentially, I'm just going to draw on the other double bonds from before. And then we can see, oh, here's our new sigma bond. Here's our new sigma bond. So our X goes right here. And so we can see that our original compounds are right here. and right here. One more thing that we should note is that we can do this type of Diels Alder reaction with a pentadiene, and that will create sort of a weird looking final product that we are not used to seeing before. So let's say that we have this guy right here. This is going to be our pentadiene, plus we'll just use just a regular double bond, 2 carbons, all that stuff. So the same thing will happen. These two will make new bonds between these carbons. This double bond will move right here. So let's just go ahead and draw our new compound. So we know that we're going to make a 1, 2, 3, 4, 5, 6 carbon ring. So what I'm going to do is I'm going to draw this in the chair conformation. So like this, or something similar to the chair conformation. So I'm going to draw it like this. So you can see here that, okay, so this is where the double bond went. Here are the new sigma bonds, and here is this guy from before. So what happened to this carbon right here? Well, it just becomes a bridge between the new form, or the new cyclic compound. And so we can see here that here is our original compound, the cyclopentadiene, and then here is the double bond. So we can see here that this sort of creates something that we aren't used to, but once we break it down, it becomes a little bit more simple. So one thing to note about this Diels Alder reaction is that these actual reactants are going to have certain names. So let's take our first example from before, which is pretty simple. So, oops, this guy right here plus this guy right here. So we can see, oops, sorry, I drew the double bond in the wrong place. So these two reactants are going to have names having to do with the Diels Alder reaction. So our diene is going to be called the diene, and then the reactant without that diene is going to be called our dienophile. I hope I spelled this right, but essentially this guy loves the diene, so it's going to create a new bond with it. That's why it's a dienophile. And one last thing to note about this whole reaction, or two things rather, it requires heat, and it also requires the diene to be in the cis conformation. It can't make a new cyclic compound if it looks like this. Oh, sorry, the dienophile has to be in the cis conformation, sorry. So it has to look like this. Wait, I'm sorry, I spoke right the first time. Please excuse me, I've had a kind of a long day of classes, but the diene has to be in this cis, or this sort of conformation. So most of the time, this isn't a problem, because most of the time, these double bonds can sort of swing around and make that double bond. However, for example, if the diene is stuck looking like this, for example, it will not be able to do the Diels Alder reaction, because there would be too much steric strain to create a new cyclic compound. So it has to look like this. It can't, and when it's like this, it would be stuck. So if it's part of a cyclic compound, it could be stuck. You can't really move it around. I'm trying to find a good example. So like this also wouldn't work very well. Okay. So let's talk stereochemistry. When we do the Diels Alder reaction, the stereochemistry will be preserved in the product. So let's say that our diene looks like this, and we have one right here and one right here. So they're both pointed. They're both pointed sort of up and in. So it's sort of hard to see, but you'll see when I finally make the final product. So this is our diene, and our dienophile is going to look like this. Yeah, let's say this. So when they come together, of course, we're going to make 1, 2, 3, 4, 5, 6. So we're going to make our cyclohexane. So I'm going to go ahead and draw everything in. I'm going to highlight our two reactants. So here's one, here's one. So how do we know what side these reactants from the beginning are on? Are they solid wedges? Are they dashed wedges? Are they what? So if they're on the same side, if they're pointed the same way, then they're going to be cis. They're going to be on the same side. So you can see here, oh, these two, they're cis. They're on the same side. So they're both going to be dashed wedges or solid wedges. I'm just using dashed wedges here. So this would be like this. Right? So that's what that would look like. However, this is a little bit harder to see. So we can see here, okay, so if I took a mirror to this, it's not a mirror on either side. So they're not going to be pointed the same way. So one is going to be a dashed and one will be a wedge. Okay? And sort of the way to tell, like I just showed there, if they're pointed the same way is, are they sort of a mirror of each other? We can see that the dienophile here is a mirror of either side, whereas the diene is not. So the substituents on the diene will be pointed in opposite ways. They're going to be trans to each other. And those in the dienophile will be cis to each other because they're pointed the same way. So yeah, I think that's about it for Diels Alder reaction. Next, I want to go on to the other paracyclic reactions, such as the electrophilic ring opening, I think it's called, but we'll get into that next time. So good luck with this stuff. Have a good day. Bye.